Okay, so the next chapter we are going to start is Exergy or available energy. This chapter is also named as availability. So in the term of availability we will come later. But before that we must know that there is a statement from second law of thermodynamics, okay, that the complete conversion of high grade energy to low grade energy is never going to be possible. Now this is a statement from second law of thermodynamics, but this concept is going to help us understand the concept of exergy, availability and available energy. Okay, so they have said that the complete conversion of low grade energy to high grade energy is never going to be possible. Okay, we have seen this several times. Okay, so energy, if you category energy into high grade energy and low grade energy, if you remember, the low grade energy was heat. Okay, that means if you give heat to a system, that complete heat is never going to get out as work. Okay, and high grade energy was work. Okay, high grade energy was work. That means heat was an non-organized form of energy and work was an organized form of energy. You can never convert a non-organized form of energy completely into a organized form of energy. Okay, that means this statement tells us that heat is never going to get completely to work, but the maximum amount of heat that can be converted to work is going to give us the available energy. Okay, that means what, if suppose there is 5 kilojoule of heat, okay, then the maximum amount of work that can be converted from that heat is suppose 3 kilojoule. Okay, suppose it is 3 kilojoule, then this 3 kilojoule is going to be the available energy. Okay, that means the maximum amount of heat that can be converted. We know that we cannot complete the whole one, but whatever is remaining, that means whatever heat is there, from that there is a maximum amount which could be taken out as work. That maximum amount is known as a available energy. Okay, and the remaining part, okay, the remaining part or the minimum amount of heat that is, or the minimum amount of heat that is going to be, that we need to reject, is known as the unavailable energy. Suppose this is the total energy. Now there could be a maximum amount of heat. Okay, this is the total heat. Okay, this is the total heat. Suppose from that the maximum amount of heat we are going to convert into work. Maximum amount of heat we are going to convert into work. Then the remaining part is known as unavailable energy. Okay, the remaining part is known as unavailable energy. Now if I am saying that this is minimum amount of heat, because it is the minimum, okay, it is the minimum amount of unavailable energy, and this is the maximum amount of heat we can convert to work. If the amount of heat that is converted to work is getting smaller, then this unavailable energy is going to get bigger. So this is the minimum energy which we need to reject from a system, so that we can get the maximum heat which can be converted to work, is known as the unavailable energy, and the maximum heat that can be converted to work is known as available energy. Okay. Okay, so the next thing we are going to read is dead state. Okay, so what is dead state? Dead state is nothing but I have written here no potential. Okay, so dead state is the state of a system when its heat and its surrounding are in equilibrium. That means when a system and its surrounding are in equilibrium, okay, then this state is known as dead state. And I have written no potential means if there is a potential, then there is only a driving force, so that the system or the process can be driven into a certain directions. Okay, suppose for heat transfer we always want to the heat always flows from higher potential to lower potential. Okay, even the water always flows from higher height to lower higher altitude to lower altitude. Okay, so everything is going from higher potential to lower potential. Now if there is no potential, suppose two bodies are having same temperature, there is no heat transfer. Okay, even if you keep water into in a same altitude, the water is not going to go anywhere. So this is the state of water which is known as dead state, because there is no potential. Okay, that means a dead state is a state which is having or a dead state is a state of a system of which is having a equilibrium with the surrounding. you can say that the temperature and pressure of the system and surrounding is going to be same, so that there is no process which is being undergone because of the absence of potential. So that state of a system is known as dead state. Okay. Okay, so now let us consider a Carnot heat engine. Okay, Carnot heat engine is what? A higher temperature reservoir is there and one lower temperature reservoir is there. So from higher temperature reservoir, a heat amount of Q in is coming out. Okay, that is the Q in is the amount of heat which are giving as input to this cycle. Okay, and Q out is the amount of heat which is being rejected to lower temperature. So when we have drawn the Carnot cycle in TS diagram, if you remember, we have said that this was the Q in, okay, amount of heat, and there it was the Q out, okay. And in TS diagram, whatever the curve is there, if you project it directly on entropy axis, this is going to give you the amount of heat transfer, okay. That means the total amount of heat you are giving as input is going to be the area under this curve, okay. Is going to be the area under this curve when projected on entropy axis. Okay, so this is the total amount of heat which you are giving from process these two. If you number this system, then from process 2 to 3, this is the amount of heat which you are giving. Okay, and from 4 to 1 heat gets rejected. From 4 to 1 heat gets rejected. If you want to remember, you can go back to the notes of Carnot cycle. There you can see from 4 to 1 this was the cycle of heat rejection. That means what? This, if this is the cycle of heat rejection, that means the area under this curve is going to be the amount of heat which is getting rejected. Okay. Now, if you see, the Q in is the amount of heat you are giving and Q out is the amount getting rejected. Now, the amount of heat which is remaining is the area between this square. Okay. Area covered by this square is going to be the amount of work, amount of heat which is going to convert it to work. Okay. This is the amount of heat which is going to get converted to work. Now we know that efficiency of Carnot engine is 1 minus TL by TH. Okay, 1 minus TL by TH. This is the efficiency of Carnot engine. Okay. Again, efficiency is what? W, which we are going to take out. Okay. W is the amount of work which we are going to take out, and in the denominator it will be Q in. That is the amount of heat we are giving in as input. Now from that we can write that W is equals to what? Q in into 1 minus TL by TH. Okay. W is the amount of Q in into 1 minus TL by TH. Okay. Now this is going to be the work done which we'll get from a system. Now what is going to be the maximum amount of work which we can take out from a Carnot engine? So for work to be maximum, that means what? Our this temperature, lower temperature has to be smaller. Okay. For a given high temperature, suppose they have given that you cannot go higher than this temperature, that is TH temperature, and you can only give this much amount of heat. You can only give this much amount of heat, and this is the temperature up to which you can go at most. Okay. Then for getting the maximum work, your TL should be low. If TL is low, then this part is going to get low. If this part is going to get low, that means what? From 1 we are subtracting a very lower amount. Okay, this part is becoming lower, that means from 1 we are subtracting a very lower amount. So that maximum part of the 1 is remaining here. Okay, so the TL or the lower temperature must be minimum, so that the work output must be maximum. Okay, now this is the TL. TL is what? If TL comes down, that means what? The area which has been covered by black patches, okay, the area which has been covered by black patches is going to get smaller, because if TL comes down, this area will be smaller. If this area is going to be smaller, that means this area is going to get bigger. This area is going to get bigger means this area is going to give you the amount of work or the amount of heat that can be converted to work. Okay, that means the remaining amount of heat which is converted to work. So to get the TL must be minimum, so that this heat rejected is minimum, so that the work output gets maximum. Now the maximum amount up to which the TL can be taken is atmospheric temperature. Okay, because if you go lower than atmospheric temperature, you need another work input so that you can maintain that temperature. Maintain the temperature lower than atmospheric temperature. A concept of refrigeration will come. Okay, so you cannot go beyond the atmospheric temperature. Okay, so the minimum amount of temperature which must be there, so that the maximum amount of work we can take out, for that TL must be T naught or T infinite, T atmosphere. Okay, this must be equal to T naught. Okay, so if this is T naught, that means the lower temperature is going to be minimum and maximum work we are going to get out. So from here we can write that W max or maximum amount which we can take out for a given Q in. You are said that you can give only this much amount of heat. More than this heat you cannot give. Okay, and given maximum temperature. Given maximum temperature means you cannot go beyond that temperature. You have a limit of maximum temperature, so this is given TH. So in such conditions, what is the maximum amount of work you can take? This is going to be T naught or temperature of the atmosphere. Okay, so in this way you can find the what is the maximum amount of work which can be transferred to maximum amount of heat which can be transferred to work. Okay, or the maximum amount of work which can be converted from the heat input which you are giving is going to be told by this expression. Okay, I hope I could make you understand from this diagram, because you can easily understand that when TL becomes lower, the area will become lower, the heat rejected is going to get lower. If heat rejection, you always know that W is equals to Q in minus QR from here, from first law of thermodynamics for a cycle. Okay, Q in minus Q. So if this is coming down, obviously this work will always go up. Okay, so Q, we need to minimize the heat rejected, and to minimize the heat rejected, that is this area, and this area to be minimum, TL should be minimum, and TL cannot come lower than atmospheric temperature. Okay, so to maintain or to lower the heat rejected, we must maintain the temperature at lower temperature at atmospheric temperature, and under this condition, this is going to be the maximum work which can be taken out from heat which you are giving as input. Okay, we are going to see the conditions for work to be maximum. Now this was the expression which you have gotten other board, okay, in the previous board. So this is the maximum amount of work which could be taken out from Q in. So this amount of work is known as available energy. I have written here it as AE. Okay, this is the amount of available energy which we are going to get if this is the amount of heat given. Okay, now for conditions, the first one is given as the cycle must be reversible. Now if you remember, we have clearly derived one expression where we could say that the reversible engine efficiency is always going to be higher. Okay, now if you bring Q in under W max, you will get efficiency. Okay, then while the efficiency is going to, if Q in is constant, okay, efficiency is what? Efficiency is nothing but W by Q in. Okay, this is the efficiency. Okay, now if Q in given is constant, okay, Q in given is going to be constant. Now for work to be maximum, the efficiency must be maximum. Okay, and if you remember, we have directly derived that only the reversible engines are going to get higher efficiencies than irreversible engines. So the first condition to get higher or the maximum work is going to be the cycle must be reversible. Okay, and the second thing is heat must be rejected at constant atmospheric temperature. Okay, so heat must be rejected at constant atmospheric temperature, then only we can get. Now temperature cannot come below below the atmospheric temperature, only it can rise. Okay, it can rise from T naught to higher. So if it is going higher, that means what? The area T naught is getting higher, that means the area below this TO line is going to get increased. Okay, that means what? If it is getting higher, then the area below this curve is going to get increased. Okay, so to keep it minimum, we must say that the heat must be rejected at constant atmospheric temperature. Okay, heat must be rejected at constant. So now this is the TO. Okay, and this is S1 and this is S2. The difference between them is going to be del S. Okay, the difference between them is going to be del S. Now what is the amount of unavailable energy here? Unavailable energy is nothing but this area. Okay, we have said it in the last board that unavailable energy is going to be your this area. Now what is the value of this area? The breadth of this is a rectangle. Okay, now the breadth of this is going to be T naught. The breadth of this is going to be T naught and the length of this is going to be T del S. Okay, so this is the unavailable energy which we are talking about. Okay, this is the amount of unavailable energy. Okay, now what? Now if you take Q in must be the summation of unavailable energy and available energy. What is the available energy here? This is the available energy. Okay, so Q in is the amount of heat which you are giving. Okay, Q in is the amount of heat which you are giving, and from that this is the unavailable energy which we are rejecting. Okay, or the unavailable energy is something which cannot be converted to work. Okay, so Q in must be equal to available energy plus the unavailable energy. Okay, this comes from the law of conservation of energy. So Q in is the total amount of heat. From that, this is the available energy and the remaining unavailable energy. That means Q in is what? Q in is the total area. Q in is the total area. From that, this unavailable energy is going out. So whatever it is remaining inside this is going to be available energy. Okay, then available energy plus this unavailable energy makes the Q in. So Q in is going to be available energy plus unavailable energy. From that you can write that what is available energy. Available energy is whatever the amount of heat you are giving minus the unavailable energy, or you can write T naught into del S. Okay, or you can write T naught into del S. From this equation also you can write. Okay, or you can write what is the available energy. Available energy is the total amount of heat you are giving minus the unavailable energy. Unavailable energy is going to get rejected, and this is the amount which will be remaining and can be converted completely to work. Okay, so these things which comes from the conclusion of whatever we have done in the previous board. Okay, so now we are going to see heat at higher temperature is going to have a greater significance. Okay, now we are going to see how giving heat to a system at higher temperature is going to have a greater significance. Okay, for example, in a system I am giving some heat at 20 degrees centigrade, and another person is giving same heat to the system at 100 degrees centigrade. Then the person giving the heat at 100 degrees centigrade is going to have a greater significance than me, who is giving that heat at 20 degrees centigrade. Okay, that means if I am giving the same amount of heat at 20 degrees centigrade, the amount of work which I can get from that amount of heat is going to be definitely less than the person who is giving the same amount of heat at 100 degrees centigrade. Okay, that means if you give heat at higher temperature, then that heat at higher temperature is going to carry more significance. Okay, so we are going to show this how the heat given at higher temperature is going to have higher significance. Okay, so we are going to show you this temperature entropy diagram. Okay, now suppose you want to give Q in amount of heat to a system. Okay, and this is heat to a system in a Carnot engine. Okay, that's why I have drawn the diagram like this. Okay, in rectangular version. So suppose you want to give some heat in a Carnot cycle, and this is the same amount of heat, and in one engine you are willing to give that heat in T1 temperature, and in another engine you want to give that the same amount of heat you want to give in T2 temperature. Okay, now before that we need to remember that I have said whenever a curve is given in TS diagram or temperature entropy diagram, when that curve is projected on entropy axis, then the area covered by that projection gives you the amount of heat. Now you want to give heat at T1 temperature, give the Q in amount of heat at T1 temperature. Okay, then what will happen? The T1 temperature means what? Here temperature is constant from 1 to 2, and this is the process where you give Q in amount of heat. Okay, now if you want to represent that Q in amount of heat in process 1 to 2, if you want to represent that heat in that graph, then what it is going to be? This will be the area covered by this one 1 and 2. Okay, 1 2 by curve 1 2, whatever the area is covered inside this when projected on entropy axis, this is going to give you the total amount of heat. Okay, now I am going to give same amount of heat at T2 temperature. Okay, now you are going to see that I have extended this diagram. Okay, initially 1 to 2 was like this. Now I have lowered down the temperature because we want to give at some lower temperature, and I have extended this. Why I have extended this? Because Q in is represented by area. Okay, Q in is represented by area in TS diagram. Okay, that means what? If you want to represent the Q in for T2, then the area covered by 1 2 when projected on entropy axis must be same. Okay, that means heat given at T1 is determined by this area. Okay, hatched in blue lines. Okay, now heat given at T2 temperature will be given by this red hatched area. Okay, this is given by this red hatched area. Okay, now I must say that for Q1 to be same, the area hatched by red lines and the area hatched by blue lines are definitely going to be same. That means the area is going to be same. Then only we can say that the same amount of Q in or the Q in amount of heat is given in both the cycles. Okay, now what is happening? We have already said that whatever the temperature is the lower one, whatever lower temperature we are using, that area under that lower temperature is going to give you the unavailable energy. Okay, in the last board we have discussed that whatever the area is under that line or under that lower temperature line, that area is going to give you the unavailable energy, because this is the amount of heat we are rejecting. Okay, this area gives us the amount of heat. Okay, this area gives us the amount of heat we are rejecting. Okay, that means what? If you consider this cycle temperature at T2, 1 dash, 2 dash, 3 dash and 4 dash, for this unavailable temperature is total this one. For cycle 1 dash, 2 dash, 3 dash and 4 dash. Okay, this is the total amount of unavailable energy. Okay, now if you want to represent the unavailable energy for cycle 1, 2, 3 and 4, for 1, 2, 3 and 4, the unavailable energy is going to be only this area. Okay, whereas for that cycle 1 dash, 2 dash, 3 dash and 4 dash, the unavailable energy was this area. Okay, that means in which case the unavailable energy is more? The unavailable energy is more in case of 1 dash, 2 dash, 3 dash and 4 dash, because the area under the lower temperature curve is going to be bigger in case of 1 dash, 2 dash, 3 dash and 4 dash. Okay, so in this way we can say that when temperature in temperature T1, when heat is given, the unavailable energy is low. Okay, low means what? Unavailable energy is low means available energy is more. That means for same amount of heat Q in, we can get more amount of available energy. Okay, this is seen from here. So this is the total amount of unavailability which is going to increase when we give the same heat at T2 temperature. This is the amount of unavailable energy which is going to get increased. Okay, or this is the loss of available energy while we are giving the same amount of heat at T2. Okay, same amount of heat at T2. Now if you want to find out what is, now let us suppose that the entropy change for the cycle 1, 2, 3 and 4 is del S, and entropy change for the cycle 1 dash, 2 dash, 3 dash, 4 dash is del S dash. Okay, now what is going to be the change in, what is going to be the loss in available energy if you consider this cycle? Okay, this would be nothing but the area, this would be nothing but the change in the bigger area. Okay, the area covered by this line. Okay, that means the total increasing unavailable energy, this is the amount of unavailable energy. So we'll get it when we will subtract this area, when we will subtract this area from this total area. Okay, so what will be the value of this area? What will be the value of this area? That means loss of available energy or increase in unavailable energy. What it is going to be? These both are going to be same. Okay, so what is this going to be? You can easily say this is the temperature T naught. Okay, or the atmospheric temperature. So you are going to say that the bigger area is T naught into del S dash. T naught into del S dash minus what area? Minus this area. Okay, this is what? T naught into del S. Okay, T naught into del S. So you can easily write T naught into del S dash minus del S is going to be the total increase in unavailable energy. Okay, unavailable energy. Now if you want to find out what is del S dash means dash means what? Whether you can consider this difference or this difference or this difference. Okay, so I am considering this difference because temperature is given here and Q in is known to us. Okay, so for del S, if you want to find out del S dash, then this is going to be Q in divided by T2. Okay, minus Q in by T1. Okay, because this is del S. Okay, this is del S. So you can say, you can take this one also, this one also, this one also. I am taking this one, this difference. Okay, because along the line the entropy change is going to be same. So we are taking this one because temperature T1 is known and whatever heat is coming in at this temperature is known. Similarly for this cycle also, we want to find the entropy change in this curve because Q in, here also Q in amount of heat is going to come. So Q in is known, that is the amount of heat which it is transferring at this temperature, at T2 temperature is also known. So we are going to find out in this way. Okay, so from here what you can say, you can take Q in common, T naught is already common. Okay, you can say that T1 minus T2 divided by T1 into T2. This is going to be what? This is going to be your increase in unavailable energy or loss of available energy. Okay, that means what? If you give heat at a lower temperature, there will be increasing unavailable energy, increase in unavailable energy. If you give heat at higher temperature, there will not be any, I mean the whatever the unavailable energy is there is going to be less than when you give the heat at lower temperature. So heat at higher temperature is going to have one greater significance. Okay, now we are going to see another question. Okay, so they have given that 500 kilojoule of heat is removed from a constant temperature of 835 Kelvin. Okay, and the heat is received by constant temperature of at 720 Kelvin. The lowest available temperature is 280 Kelvin. Find out the loss in available energy. Okay, so what they have given? They have given us the amount of heat. Okay, they have given us two constant temperatures. Okay, and they have given us the lowest available temperature, and they have asked us to find the lowest available energy. Okay, so the main thing is that a body at 835 Kelvin is giving heat 500 kilojoule of heat, and the same heat is received by another body of 720 Kelvin. Okay, now if you plot this in TS diagram, what it is going to be? They have given us a higher constant temperature of 835 Kelvin. Okay, a slightly lower temperature of 720 Kelvin. Okay, now they have said that 500 kilojoule of heat is going to be given away by a body at 835 Kelvin. Now suppose this is the temperature, okay, 835 Kelvin, and this area, whatever the area it is going to give, this area is going to be equal to 500 kilojoule. Okay, that means there are some heat interaction through this process, 1 to 2, through this process some heat interaction is going on. Okay, and what is the amount of heat transfer that is going on? That must be equal to the area of this curve when projected on entropy axis. Okay, now they have said that the same heat, okay, that means another, at another temperature 720, they have given 720 Kelvin. Okay, at 720 Kelvin the same amount of heat is been received by another body. That means at 720 degree centigrade, 720 degree Kelvin, another body at this temperature is receiving the same heat. Receiving the same heat means the area covered, suppose this is 1 dash and this is 2 dash. Okay, now when area of 1 2 is projected on entropy axis, whatever the area it is getting, the amount of area would be same when 1 dash and 2 dash is projected on entropy axis, because they have mentioned that same heat. Okay, 500 kilojoule is given away by a body at 835, and again 500 kilojoule of heat is received by body at 720 degree Kelvin. Okay, now they have given us that the lowest available temperature is given as 280 Kelvin. Okay, lowest available temperature is 280 Kelvin. So this is the lowest available temperature. So now they have asked us to find what is going to be the loss in available energy. Okay, so loss in available energy is something which you have found out in the last board. Okay, so this formula was given as Q in into T naught to T1 minus T2 divided by T1 into T2. Okay, now this is given as T1, this is given as T2, and this is T naught. Now if you put the values, what it is going to be 500 into T naught is what? T naught is 280 Kelvin. T naught is 280 Kelvin. What is T1? T1 is 835 minus 720. T2 is 720 divided by 835 into 720. Now what is going to be the answer? The answer is going to be 26.78 kilojoule. 26.78 kilojoule. So in this way you can find out the loss in available energy. Okay. Okay. So the next thing we are going to read is availability. Now what is availability? Availability is the maximum amount of work which can be derived from a process. Okay, and in that process the final state of the system must be in equilibrium with the surrounding. That is, the system must be in dead state. We have discussed dead state earlier. What does a dead state means? Dead state means in that state the system and the surrounding are in equilibrium. That means no potential is there and no further reaction is going to take place. Okay, that means there is no other driving force to change its state from the dead state. Okay, so to make you understand, I will say this again. Availability is the maximum amount of work which can be derived from a process. Okay, and in that process the final state of the system must be in equilibrium with the surrounding, and in that process whatever the maximum work that is derived is known as availability. Okay, now what is the difference between availability and available energy? We have read available energy, okay, and we are reading availability. Now availability is something which is considered for a process. Okay, availability is something which is considered for a process, and available energy is something which is considered for a cycle. Okay, so now what we are going to do, we are going to find out what is the maximum W max we are going to find out. Okay, W max. W max means what? W max means the net work which we are going to get. Okay, in certain processes what is going there. In certain processes the system does some work. Okay, the system does some work. Okay, suppose in a piston cylinder arrangement is there. Piston cylinder arrangement is there. Okay, from that, if you heat up the gas, what will happen? The gas will expand and the piston will go up. That is the work done by the system. Okay, but here some atmosphere atmosphere is there, and for that atmosphere what is happening, it is trying to, whatever the atmospheric pressure is there, it is trying to pull down the or push down the piston. Okay, push down the piston, and this gas is trying to pull up the piston. Okay, now what is going to happen, there is going to be a net work. Okay, if the work done by the atmosphere is higher, or is going to have a higher value, then the piston will come down. Okay, then the net work will be on the system. Okay, and if the work done by the gas is greater than whatever work is done by the atmosphere, then we are going to get a net positive work. Okay, and that net positive work could be done by the system. Okay, if work done by the atmospheric pressure is greater, then work will be done on the system. Okay, now that means what, we, for finding the maximum net work, we are going to subtract W, we are going to subtract W surrounding. Okay, that is the work done by the surrounding from work done by system. Okay, to get the maximum work, what we will do, we will we will subtract the W surrounding. That means whatever the work is done by the atmospheric pressure from the whatever work is done by the system. Okay, whatever the work is done by the gas. Okay, now then only we can find the expression of W max. Okay, now up to this we have found out what is W system. Okay, whatever the work is done by the system, we are going to find in this board. In the next board, we are going to find what is going to be the W surrounding. Okay, what is going to be the W surrounding, and by figuring out what is W surrounding, what we will do, we will subtract this W surrounding from this value. Okay, from this value we are going to subtract W surrounding, then whatever the expression we are getting, that would be W max, and W max is nothing but the availability. Okay, availability in a process. Okay, now how did we find this one, W system? Okay, or work transfer in a work transfer by the system. So to start with, we are going to start from second law of thermodynamics. Okay, this is impossible to find without the combination of first law and second law. So first of all, we are going to see what we have done by this second law. Okay, now in this second law we have done something. Okay, in second law we have found out that the change in entropy of an universe is never going to decrease. Okay, is never going to decrease, so it is always greater than or equal to 0. Change in entropy of universe is never going to decrease, so it is greater than or equal to 0. Now I have considered this as reversible process. In reversible process, what happens, if you break down the del S universe, what you are going to get, universe is divided into two parts, system and surrounding. So we are going to get change in entropy in surrounding plus change in entropy in system is going to be equal to 0. I would have written greater than or equal to 0, but I have considered reversible process, that's why I have written equal to 0. Now why I have taken reversible process here? Now if you remember, in the conditions of maximum work, I have given two conditions. Okay, the first condition itself says that the system must be reversible, and the second condition says that the heat rejection should be at constant atmospheric temperature. Okay, so this reversible process has been taken keeping in mind that for maximum work output it is going to be a reversible process. So we are taking reversible process. Now as this is going to be 0, we can easily write del S surrounding is going to be minus del S system. Okay, del S surrounding is going to be minus of del S system. Okay, and from this we can write dq surrounding is going to be, that means whatever heat is given by the surrounding, or whatever heat is given by the surrounding to the system, or whatever heat the surrounding is receiving from the system, is going to be whatever the heat the system is giving, or whatever the heat the system is receiving from the system. Okay, that means the heat given by the system would be the heat received by the surrounding, or heat rejected by the system would be the heat absorbed by the surrounding, or whatever the heat is given by the surrounding is the amount of heat which is received by the system. So the magnitude is going to be same, only the sign is going to change. Suppose the surrounding is releasing energy. Okay, surrounding is releasing 5 kilojoule of heat. Okay, so dq would be -5 because it is giving away the heat, and the same heat is being received by the system. Okay, received by the system means it is going to be positive. Okay, so it is going to be -5 of system. Okay, so we are getting -5 and -5 both the sides. Okay, so ultimately we will say that the magnitudes are going to be same for system and surrounding heat transfers, but the sign is going to be opposite. Okay, because one is receiving and one is giving. And how could you find the del S surrounding or change in entropy of a surrounding? It is nothing but dq by T naught. T naught is what? Atmospheric temperature. Okay, then obviously the surrounding temperature, only the surrounding entropy could be found out with the help of heat given by the surrounding or heat received by the surrounding divided by the temperature of the surrounding. This is going to give you del S. Okay, now coming to the first law. What is happening in first law? Now this is, since we have said that availability is for process, we are finding out the process first law equation for a process. I have also said this earlier that for first law, for process and for cycle, there are two different equations of first law. Okay, for cycle it is total net transfer is going to be equal to total work transfer, and for first law it is going to be the total heat transfer is going to be change in internal energy plus whatever the work transfer is there for process. Okay, this is for process. Since availability is for process, so this we are finding for process. Okay, now what is going to be there? We have found out dq, or keeping the dq in one side, we are taking all the other expressions on other side. So we have taken dw system in one side and others on another side. So this will come, if this comes this side, then this will become negative. Okay, that's why minus du system plus dq system is going to be your dw. Okay, now since it is minus du, what is going to be that dw system is going to be, generally du means final internal energy minus initial internal energy. Now since on minus is there, so we are reversing that. It is going to be initial internal energy minus final internal energy. Okay, plus dq system. Okay, this is going to be dq system. Now the same thing has been written, only the dq system has been changed to minus dq surrounding. Okay, that means this one we have applied here. Okay, dq surrounding is going to be minus dq system. We are writing dq system is going to be minus dq surrounding. Okay, now from here you can easily write now dq surrounding is what? If you see from here, what is going to be the dq surrounding? Dq surrounding is nothing but T naught into ds surrounding. T naught into ds surrounding. But we have, for the sake of simplicity of what we are finding, okay, because whatever entropy values will be given, okay, will be given for the system. We'll have the entropy values for system. So we are ultimately going to find out the expression for system. So what has been done here? First of all, this dq system has been changed with minus dq surrounding. Okay, dq system has been changed with minus dq surrounding. Now from here you can say that dq surrounding is going to be what? Nothing but T naught into ds surrounding. So this could be minus of T naught into ds surrounding. Okay, but again it is written here minus system, but you can see that ds surrounding is what? Ds surrounding is minus of ds system. So in place of writing ds surrounding, I am writing minus ds system. Okay, this is the only thing. Okay, dq surrounding is T naught into ds surrounding, and in place of ds surrounding we are writing minus ds system. Okay, only this is the difference. Now since again this is minus here, minus ds, generally ds is what? S2 minus S1. Now here since minus is there, we are going to write S1 minus S2. So the final expression of W system is going to be what? Final expression of W system is U1 minus U2, same thing. Okay, same thing has been repeated. Minus is there, T naught is there, but within the bracket, in place of S2 minus S1, I am writing S1 minus S2 because one negative sign is there. Okay, so from this board, this part has been done. This part has been done. Now in the next board we are going to see what is going to be W surrounding. Once we find W surrounding, we can subtract this W surrounding from W system, then we are getting W max, which is our requirement. W max is what? The value of availability. Okay, the final expression of W useful. Now if you break down each and every part, the thing which you are going to get is U1 minus T naught into S1 minus plus P naught into V1. Okay, and in that side you are going to get the remaining part, which is minus of U2 minus T naught into S2, okay, and minus P naught into V2. This is the expression which you are given. To make it simple, they are writing this total thing as phi 1 and they write this total thing as phi 2, so that we can directly write W useful is going to be equal to phi 1 minus phi 2, where phi 1 is what? Phi 1 is U1 minus T naught S1 plus P naught V1 minus U2 into T naught S2 plus P naught V2. Okay, so this is the W useful or useful work which you can get from a closed system. Okay, so previously we have found out the availability in closed system. Now we are going to find availability for closed system. Now whatever the second law expression was there for the closed system, it is exactly same we have done here for open system. This is again going to be same. Universe greater than equal to 0, we have taken reversible, that's why we have taken equal to 0. Del S universe, if broken down, it becomes system plus surrounding. Okay, now this system becomes minus of surrounding. Similarly, the heat transfer will also become minus of surrounding. For system is going to be minus of surrounding. And how are you going to find the ds surrounding? It is nothing but dq by t naught of surrounding. Okay, so this part is completely same for whatever we have found out availability for closed system. Okay, now it is availability for open system. Now if you remember, the first law equation for an open system was this one. Okay, enthalpy plus V1 square. This was per unit kg. Okay, kilojoule per kg. Okay, so this one is what? H1 plus V1 square by Z1. This one was enthalpy. This one was for kinetic energy. This one was for potential energy. This one was the heat transfer. Okay, and here also same, the final enthalpy, then kinetic energy at final position, potential energy at final position, and this was the W system. Okay, whatever the work is done by the system. Now we are neglecting the effects of kinetic energy and potential energy. We are neglecting the effects of kinetic energy and potential energy from both the sides. Now whatever it is remaining, the remaining thing is W system is equal to H1 minus H2. This H2 will come out this side. So W system is going to be H1 minus H2 plus the remaining thing is Q system. Okay, this one is equal to H1 minus H2 plus Q system. Okay, now Q system is what? Q system is nothing but this is Q minus of Q surrounding. Okay, DQ system is going to be minus of DQ surrounding. Here it is capital letter. Okay, here it is capital letter. That means here we have written small letter q because we have taken out per unit mass. Per unit mass becomes small q. Otherwise the concept is going to be same. DQ system is going to be minus of DQ surrounding. DQ system is going to be minus of DQ surrounding. Okay, now W system is what? How can you find DQ surrounding? DQ surrounding is nothing but T naught into DS surrounding. T naught into DS surrounding. Okay, again DS surrounding is what? DS surrounding is minus of DS system. DS surrounding is minus of DS system. So like the previous one only, what we have done, we have done the same thing here. Just in place of surrounding, we have written minus of DS system. Now since it is the minus of DS system, minus of system means S1 minus S2. If minus was not there, it was S2 minus S1. Since there is minus, we have written S1 minus S2, and the remaining H1 minus H2 is completely same as this one. Okay, now in open system the surrounding does not give that much work into a system. Okay, so we are not considering the W surrounding. So in an open system, whatever the W system we are getting, this is the maximum amount of work which we are going to take out from an open system. Okay, now if you break down this equation, okay, this is the amount of W max or W useful, okay. So if you break down this equation, what you are going to get? You are going to get H1 minus T naught of S1 and H2 minus T naught of S2. Again, this part is known as psi 1 and this part is known as psi 2. Previously for closed system it was phi 1 minus phi 2. Now it is psi 1 minus psi 2. So W max is going to be psi 1 minus psi 2. Okay, now if you clearly notice, there is a pattern to remember this. Okay, this is for open system. For open system you will have to consider the enthalpies, okay, and in the closed system you have to remember about the internal energy, because there was U, okay, there was U, now there is H, okay. So here you need to remember enthalpy minus T naught into S1, and there you need to remember internal energy minus T naught into S1, and there was an addition of there is an extra term of W surrounding. W surrounding is P naught into V1 minus V2. So if you directly subtract that W by surrounding or work done by the surrounding, then you can easily get the pattern. Okay, how to remember the maximum useful work for an open system and maximum useful work for a closed system. Okay, in open system there is enthalpy, and in closed system there is internal energy. Only thing is that in the closed system you needed to subtract the W surrounding. If this you can do separately, then exactly the formulas are going to be same. Just in place of H1 you can replace it by U1 and U2. Okay. Okay, so the next topic we are going to start is irreversibility. Okay, so the concept of irreversibility is going to be understood by these diagrams. Okay, so first of all let us consider I have this much amount of total heat. Okay, this much amount of total heat is available here. Now we have also seen that total heat cannot be converted to work. Okay, so there is a maximum amount of heat which can be converted to work, and the remaining part is known as unavailable energy. Okay, from the total heat, this portion is unavailable. Okay, and this portion of heat is available. Okay, so this is known as the available energy, or this portion of the heat which is completely converted to work. Okay, so here we have written available energy or W reversible. W reversible we are saying that because all the expressions of work were derived considering two conditions. First condition was that the cycle must be reversible, and the second condition was that heat must be rejected at constant atmospheric temperature. So considering the first condition, that is to get the maximum work, the cycle must be reversible. So we are directly writing that whatever available energy is there is going to be your W reversible, okay, or work done in a reversible process. But we know that actual work is always less than that of idealized reversible work. Okay, the first one, actual work is always less than the idealized reversible work. Okay, so this is the reversible. That means theoretically, okay, theoretically while we are considering all the reversible processes, then we are getting this much amount of heat. But when you are going to actually give the heat, is this the same amount of work we are going to get? No, because whatever we are going to give is going to be irreversible, and actual work is always less than that of ideal reversible work. So in actual case, what we are getting in actual case, out of that AE or W reversible or work reversible, out of that the full amount of work we are not going to get. Okay, so leaving the unavailable energy, this is the unavailable energy. Okay, leaving the unavailable energy, whatever the W is remaining, we are going to lose this much amount of work. Okay, this much amount of energy we are going to lose. Okay, because actual work is always less. Actual work is always less than the W reversible or available energy. Okay, or reversible work. Okay, so the difference between the W reversible and W actual is going to be this portion. Okay, and this portion is known as, this portion of heat is known as irreversibility. Okay, so irreversibility, if we take irreversibility as I, we can say that irreversibility was W reversible minus W actual. Okay, so this This is the available energy, or this is the part of the heat which can be converted to work reversibly. Okay, now if we go in actual world, then what will happen? This, the total W reversible we are not going to get. We are going to get only this amount of W actual. Okay, so where did the remaining of the heat or the remaining of the energy has gone? This is the remaining of the energy, and this part is known as irreversibility. Okay, and they have clearly said that the difference between these two, okay, actual work, the actual work is always less than ideal reversible work, and the difference between these two is known as irreversibility. This is the difference. This is the ideal reversible work, and this is the actual work, and the difference between these two is this portion, and this portion is known as irreversibility. Okay, okay, so we are going to see Gauss-Stoddler theorem. Okay, so what did he say? His theorem states that the rate of loss of available energy, or the rate of increase of irreversibility, is going to be directly proportional to the rate of increase of entropy of the universe. Okay, so as we have seen, if this was the total heat, this was the unavailable energy, and this part was the irreversibility. Okay, and if this part was not there, then this was available energy. Okay, if this is the available energy, now in irreversible is what? Irreversibility is 0. Irreversibility is 0 here. Now as irreversibility is slightly going to increase, okay, with the increase of the irreversibility, there will be decrease in the available energy. Okay, so they have said that the rate of loss of available energy, or the rate of increase of irreversibility, if available energy is going to decrease, the irreversibility is going to increase. Okay, and it is directly proportional to the rate of increase of entropy of the universe. Okay, so we can directly write that if irreversibility is denoted by I, then it is directly proportional to the del S universe. Okay, and del S universe is never going to get decreased. Okay, so from this relation we are going to find out an expression for irreversibility which would be better for our calculations. Okay, okay, so we have seen that irreversibility is what? Irreversibility is the difference between the reversible work or the available energy and the actual work which you are getting. The difference between them is known as irreversibility. Okay, now irreversibility, W reversible is what? W reversible is nothing but the available energy. Okay, so if you remember, we have found out the available energy by system. Okay, except the surrounding is going to be this one. Okay, U1 minus U2. In the expression which you have derived, it was written as minus T naught S1 minus S2. Now since we have written S2 minus S1, the negative sign has become positive. Okay, we have taken S2 minus S1 so that we can write del S. Okay, del S is always S2 minus S1. We have written this so that we can write del S. Okay, and we are subtracting the W actual. Now what is going to be the W actual? W actual is difference in or change in internal energy plus the Q actual, negative of change in internal energy plus Q actual. Okay, so if you see, it has come from the first law of thermodynamics for a process. So in first law of thermodynamics for a process, you will see that dq is equals to du plus dw. Okay, so what is going to be dw? Dw is going to be minus of du plus dq. If this comes this side, then it will be negative. Okay, so since it is negative, since negative sign is there, that's why we have written u1 minus u2. Okay, and we have given a positive sign in the front. Okay, because always du is going to be u2 minus u1. Now since it is negative, we have written u1 minus u2. Okay, now this is the q actual. Now in the next line, what we have done, you will see that here u1 minus u2 minus u1 minus u2. Okay, so these two terms will get cancelled. Okay, now the remaining part is what? T naught into del S system. Okay, T naught into del S system minus Q actual. Okay, now Q actual is what? If you suppose there is a system. Okay, now the amount of heat you are giving is going to be equal to the Q of system. Okay, that is the amount of heat received by the system is going to be Q actual. Okay, now the amount of heat that is received by the system is also the amount of heat which is given away or rejected by the surrounding. Okay, it's the same amount of heat, only the direction will be opposite. So this thing we can write as minus Q of surrounding. Okay, because this Q system is the amount of heat, or Q actual is the amount of heat which you are giving to the system. Now if you are giving to the system, that means what, the same amount of heat is being rejected by the surrounding. So Q system is going to be equals to minus of Q surrounding. Okay, so we have written down Q surrounding here. So here it was negative sign because negative sign was there. So here it was negative sign. I have made it again another minus will make it positive. So Q actual I have written it as Q surrounding. Okay. Now again, what is Q surrounding? Q surrounding, that means in the last lecture what we have found out, we have found out that ds is going to be dq by t naught. Okay, for surrounding. This is for surrounding. Okay. Now dq is what? dq is the amount of heat transfer. Now the amount of heat transferred is q surrounding. So from here dq surrounding we can write it as T naught into ds surrounding. Okay, T naught into ds surrounding. So same thing we have written, T naught into del S surrounding. So the final expression has become T naught into del S system plus T naught into del S surrounding. Now take T naught common. If you take T naught common, you will get del S system plus del S surrounding. Now that system plus surrounding gives you the del S of universe. Okay, this system plus surrounding gives you the del S of universe. So finally we can say that now T naught here is constant. T naught here is going to be the atmospheric temperature and it is going to be constant. So we are finding that I is equal to T naught into del S universe. So if T naught is constant, that means we can write that I is equals to I is proportional to del S universe. Okay, this is what? This is nothing but the Gauss-Todela theorem. Okay, now with this we are completing our availability chapter. Okay.